lattice figure shows the cubic crystal structure of sodium chloride. BaCl. Schematic representation of the cubic crystal structure of sodium chloride. You see the almost restrict the stable. The content, which is filled with a certain number of gas molecules. First, the state or the variable of them. The first of all is the volume of it. Then the number of the overall molecules and the pressure. The pressure on the surface of the container. And finally, temperature. As a matter of fact, in a microscope, the pressure and the temperature have so close relationship. As you can see, when some heat into the container of the gas, the temperature of it will increase. And the temperature increase, which means the speed of the molecules increased. Then the speed increased, and the molecules that are heated on the surface of the container increased. The force that the molecules give the container get larger. And that is how the pressure comes from. Now we are going to calculate in a microscope how the molecules, the movement of it, result in the pressure of the gas. During collisions, the molecules exert force on the walls of the container. This is the origin of the pressure that the gas exerts. In a typical collision, the velocity component parallel to the wall is unchanged, and the component perpendicular to the wall reverses its direction but does not change in magnitude. Our program is first to determine the number of collisions that occur per unit time for a certain area A of the wall. Then we found the total momentum change associated with those collisions and the force needed to cause this momentum change. From this, we can determine the pressure, which is force per unit area, and compare the result to the ideal gas equation. As you can see in this figure, we can figure if in a two-dimensional situation, the force of the velocity or the speed of the molecule can be at any direction. When the collision happens, we divided the speed to two components. The first one is a Vx. Second one Vy. And Vx plus Vy equals to V0. Vx is that parallel to the x-axis or vertical to this wall. And the second one, Vy, is the velocity of it parallel to this wall. When the collision happens, the Vy remains unchanged. However, Vy remains unchanged, which is exactly the same before the collision. However, the Vx has changed in direction, before the collision, after the collision. Therefore, the momentum of the molecular has changed. We will find a direct connection between the temperature of the gas and the kinetic energy of the gas molecules. To begin, we will assume that all molecules in the gas have the same magnitude of x velocities, Vx. Of course, it isn't right, but making this temporary assumption helps to clarify the basic ideas. We will show later that this assumption isn't really necessary. Or with the same velocity in the x-axis. It isn't right, but we can make it easier to understand. As shown in figure, for each collision, the x component of velocity changes from Vx to minus Vx, or from minus Vx to Vx. No matter the symbol it is changed in direction and remain the same in volume. So, the x component of momentum changes from minus mvx to positive mvx, and the change in the x component of momentum is 2 mvx. We can say delta T variation in the momentum is 2 mvx. If a molecule is going to collision with a given mole area A, during a small time interval delta T, then at the beginning of delta T, it must be within the distance Vx dt from the wall, and it must be tended toward the wall. In the time of delta T, if the collision happens at the exact time of 0, which means before the collision, it is with the distance of dt Vx away from the wall. That after the dt, it will touch the wall. And it must tend toward the wall, otherwise it will get away from the wall. So the number of molecules that collides with the wall A during the T is equal to the number of molecules within a cylinder with base area A and the length Vx dt that have the x velocity m toward the wall. The volume of such a cylinder is A Vx dt. Vx dt. In a certain period of time, dt, there are some collisions of the molecules on the wall, and there's two conditions to make sure that the molecule will have a touch of the wall during the time of dt. The first of it is during here. Their x velocity m toward the wall. They have to move to get close to the wall. Otherwise, no collision will happen. Then it should be close enough to the wall. If it is far away from the wall, even though it is getting closer, In a period of time dt, the collision won't happen. Therefore, two conditions have to be fulfilled in the same time. First, towards the wall. Second, it is close enough to the wall. Assuming that the number of molecules per unit volume, n divided by v, is uniform. The number of molecules in this cylinder is n v dx. That is your certain volume, and the volume times the density of the number of molecules. We got the overall, the volume times the density, got the overall number of the molecules in this volume. On the average, half of those molecules are moving toward the wall and half are moving away from it. So we have to divide it by 2 half of it. Because only the average, or statically, only half of the molecules in this volume is tend toward the wall, and the rest half is get away from the wall. Because there's only two directions of the react. It is close, it is hand the wall or away from it. Only two choices. Statically, it is half. Overall number that will do the collision during a period of time can be write like this. Number of molecules which will have a collision on the wall during a period of time dt. If the number is known, we times the number and the p, we got the overall variation in the momentum caused by the molecules during a period of time dt, as shown here. Do the production of the number and the variation of the momentum for each molecule, and the final result is A. dpx equals to A vx dt. The overall number in the container, the overall volume of the container. A is the area of the related cylinder. M is the mass of each molecule. Vx is the speed of each molecule in the x-axis in the period of time of dt. If someone remembers, delta p equals to mv, and equals to fdt, Variation in the momentum equals to the variation in the momentum and the production of force in the time. Then we continue. For the system of all molecules in the gas, the total momentum change dp during period of time dt is the number of collisions multiplied by the 2mvx. We wrote Vx squared rather than Vx squared with only the positive volume in the final expression, because the square of absolute volume of a number is equal to the square of that number. The rate of change of momentum component Px is change of the momentum equals to the force exerted by the known area A. As I write, delta P divided by delta T equals to force, or delta B equals to the production of force and dt. We have learned in the last semester. From Newton's third law, this is equal to and the opposite to the force exerted on the wall by the molecules. Pressure P is the magnitude of the force exerted on the wall per unit area, and we obtain P equals to the pressure. So we divided the force by the area A. We got the pressure divided by A, the pressure A equals mVx squared plus V. The pressure exerted by the gas depends on the number of the molecules per volume, or the density of the number of molecules. The mass m per molecule and the speed of the molecules, 3 parts. Density of molecules in number, the mass of each molecule, and the speed is the x-axis of the molecule. The final equation put it here. P equals to divided F by A and V times mass of each molecule and the Vx squared of the molecule. Now, according to this equation, we can do lots of calculations. For example, a beam of electrons moving in the positive x direction impacts a target in a vacuum chamber if 1.225 times 10^14 electrons traveling at a speed of 3 times 10^7 meters per second strike the target, drawing each brief pulse lasting 5 times 10 minus 8 squared. What average force is exerted on the target during the pulse? Assume all the electrons penetrate the target and are absorbed. Therefore, the number or the volume or the density of the electrons is known, and the speed, the Vx of it, is known. Then last 5 times 10 minus 8 times, the time is known. Oh, that is easy to do. What average force is exerted on the target during the pulse? What we want to calculate is the force. Force can be calculated by using the equation as shown here. The force on the target is equal to the negative of the change in the momentum of each electron multiplied by the number n of electrons that divided by pulse duration. Substitute the expression delta P equals to mVf minus mVi, and we know the electrons penetrate the target and are absorbed, which means after the collision, the velocity of the electrons equals to zero, which means Vf equals to 0. And then the delta P equals to minus mVi, by the solution. If the force equals to dP by dt, variation in dp, that is number of the related molecules that do the collision or that do the adsorption, then times the variation in the delta P of each molecules, and this equals to the overall variation in the magnitude, then dt. As a result, the equation here divided both sides by dt. And the f will equals to the variation in the magnitude of each electron times the number of the overall electron divided by delta t. In this equation, no matter the velocity before the adsorption is known, and the n, the number of the electrons, is known. The number is given by the question as shown here. And the delta t, the time, is given, and it is 5 times 10 minus 8 seconds. Therefore, all the parameters is known. Just put the numbers in. The speed, the mass of the electron, the variation in the speed, and divided by the time. That is 5 times 10 minus 8. Finally, we got the result 0.0683 Newton. 63 Newton. So, then question number 2. What average pressure is exerted on the base board which has a radius 4 millimeter? The base board is the region of the target struck by the beam. Pressure can be rewritten by P equals to the force divided by the related area. Thus, if we want to do the calculation of the pressure, we want to know the force and the area. And luckily, the force has already been obtained, and the area is given by the question, and that is has a radius of 4 millimeter. The radius is known, and pi r square equals to the area. Thus, P pressure equals to dividing the force by A, the area, and the A can be calculated by pi r square. The final result is 1.36 times 10³ Pascal. This is an interesting question. We have translated in microscopic the movement of the electron, and then we calculate some macroscopic properties such as the force and the pressure, which means, as a matter of fact, the pressure of the caused by the gas resulted from the variation in the microscopic of each molecules, and its variation in the magnitude. We mentioned that V8 is really not the same for all the molecules, but we could have sorted that molecules into groups having the same Vx within each group. Then added up the resulting contributions to the pressure. The net effect of all these is just to replace Vx squared in equation by the average value of Vx squared, which we denoted by Vx squared in average. We put an AB here. Furthermore, Vx squared in average is related simply to the speed of the molecules. The speed of any molecule related to the velocity components Vx, Vy, and Vz can be calculated for the overall velocity square V average will equals to the velocity in x-axis square V average and the Vy square V average and the Vz square V average. Thus, we will see the temporary assumption of that all the velocity in the x-axis of all molecules equals with each other. This has nothing to do with the final result. But there is no real difference in our model between the x, y, and z directions. Molecular speeds are very fast in a typical gas, so the effect of the gravity and equals more. It follows that with x squared in average, with y squared in average, and with z squared in average must all be equal. Hence, the Vx in average, V squared equals to 3 Vx squared. Yes. Then we can do a revision. We will replace the Vx squared by the overall velocity of the molecule. That is more easy to understand. To replace the Vx squared by 1 of 3 V squared in average. It's shown here. If you remember, the n times the V squared is part of the kinetic energy of the molecule, and the kinetic energy of the molecule is half mv squared in average. The product of this and the total number of molecules n equals to the total random kinetic energy kTr. Pv equals to n. Kinetic energy of one molecule, the number of the overall molecule, 2 of 3, is our final equation, equals to PV, pressure times velocity, times volume. Then we do a rewrite. We rewrite here by K, and the NK to KTR. And the KTR is the total random kinetic energy of the translational motion of all the molecules, because it is equals to this part. And this part is a production of the number of the overall molecules and the kinetic energy of each molecule. Now, we compare this with the ideal gas equation. This equation to the ideal gas equation. We will find the PV will equals to the nRT and equals to the 2 of 3 KTR. We do then nRT will equals to the 2 of 3 KTR, or KTR equals to 3 of 2 times nRT. In this equation, we will find this remarkably simple result shows that the kinetic energy of the overall molecules is directly proportional to the absolute temperature T, because except the time T, the N and the R and the 3 of 2 is constant if for a constant amount of molecules. The only one variable is the temperature, which means the average kinetic energy of the overall molecules depends on only the temperature. Also, total number of the molecules n is the number of the molecule of the moles n multiplied by Avogadro's number Na. Thus, the large n, which means overall number of the molecules, equals to the multiplication of the number of molecules in mole and the Avogadro's number. Then we can do the transformation. And finally, K, the Boltzmann constant. We divide both sides of the equation by the Avogadro's constant, which means we divided the overall to the number of it. Therefore, the final result is for each molecule, and the K means the derivation of the arc by the Avogadro's constant, as shown here. K TR equals to L, and we have the average, and the final equation is K is L, and we have the average equals to 3 over 2 KT, and the K is the Boltzmann constant. This shows that the average translational kinetic energy per molecule depends on only the temperature, not on the pressure, the volume, all kind of molecule. We can obtain the average translational kinetic energy per molecule by multiplying by the Avogadro's number and using the relation at the large n, the mass of the overall molecules equals to the Avogadro's number times the mass of each molecule. And the final result, the translational kinetic energy of a mole of ideal gas molecules depends on only T, temperature. Finally, it is sometimes conventional to rewrite the ideal gas equation on the molecular basis. We use the large n, the overall number of it, equals to the Avogadro's constant times the number of it in mole, and the R, large R, equals to the Avogadro's constant times the K, to obtain the alternative form of the ideal gas equation. PV equals to NKT. P3 equals to NKT. No matter how difficult it is to obtain this equation, as you can see, the only variation in this equation is first, this part, the kinetic energy, or the velocity of the molecule. On the right, constant, and the temperature in Kelvin. We can do the assumption when the temperature equals to 0. On the right, the overall part equals to 0. On the left, the kinetic which means the velocity of the molecule equals to 0. That's why there is the K equals to 0 is the minimum of the temperature in our universe, because it means if a material is with a temperature of K equals to 0, which means the molecules that consist the material remains accurately constant. There is not at all of the movement of the molecules that consist the materials. Thus, its temperature is a minimist. Or we can say the temperature is a microscopic, is a movement or the vibration or some other kind of movement like the transformation or vibration or rotation of the molecule. Briefly, the movement or the change in the place of the molecules. When the molecule remains exactly stable in an exactly place, which means its temperature equals to 0. There is an example question. What is the average translational kinetic energy of a molecule of an ideal gas at a temperature of 27 centigrade? First of all, before the calculation, if we see a centigrade, first of all, we have to translate it to the temperature in Kelvin, right? Thus, we do the addition. Of the 27 centigrade and another 273 Kelvin, and the final result is 300 Kelvin. Then we can use the question equation. What do we want to know? The kinetic energy of it, and it equals to 3 of 2 kt. K is a constant, and the only variable is the temperature. Put the temperature of 300 Kelvin here. Then we got a result. Thus, the average translational kinetic energy of a molecule is 6.21 times 10 minus 21 joule. And what is the total random translational kinetic energy of the molecules in 1 mole of this gas? 1 mole, we just need to do a production of another Avogadro constant. And the Avogadro constant is 6.02 times 10 23. Here, 1 more. LNRT. Constant. Temperature is known. And the only unknown is the 1 mole. R is known. The final result is 3,740 joule for 1 mole of the gas. Okay, this graph, we have learned the pressure of the gas in a microscope, which is resulting from the variation in the magnitude that the molecules have collision with the wall of the container, which is exactly the same as that of liquid. Exactly the same as we show in this figure. It's different from that of the liquid and from the solid.